Hello, my name is Jazaeri. I'm here to present our paper, Impacts of Residential ISA Storage Systems on Low Voltage Networks. This paper was written with my co-authors, Tansu, Alpcan, and Robert Gurdon, who were my supervisors during my PhD at the University of Melbourne. In this presentation, I will go through the introduction and give a context of the project. And then I will talk about the linear models that I have used in this study. I will touch on the receding horizon optimization framework that I used for the case study. And at the end, I'll talk about the case study itself and some of the results that I find to be very interesting. So about the introduction, the residential buildings, a lot of them have solar and a lot of them have air conditioning systems. And these systems, these especially air conditioning systems, provide flexibility to power distribution by enabling shifting the electricity demand from peak periods to off-peak periods. Cold storage is a low-cost solution that can significantly increase load shifting capabilities of air conditioning systems. It is important to understand, however, the impact of residential cold storage systems on low voltage networks, because if it's not orchestrated correctly, it can actually have a reverse impact on the network and makes the situation even worse for the networks. So to do that, we need to have an electrical and thermodynamic model that brings together the electrical set of equations and the thermodynamic set of equations into a single model. The contributions of this paper, one of them is the proposing in this paper, we are proposing a joint electrical thermal model that enables modeling the thermal performance of a house on an electrical low voltage network. And a model of the house is presented at the figure on the top. So you have your house, the ISA storage system, that is your cold storage, and the air conditioning system. The second contribution is modeling impacts of small size residential ISA storage systems on electricity peak reduction in low voltage networks. So in a network that you have a number of these systems on it, we want to model and quantify the impact of these models on reducing the peak demand. We are also quantifying the impact of ISA storage systems on voltage profiles of these low voltage networks. As voltage of the low voltage networks is one of the constraints that the networks need to make sure the voltage as always is within a bound. So the models that we have used, there are three of them. So the first one is the model for the distribution network. Here we use the dist flow model. This model was verified by a nonlinear model simulation in OpenDSS. The equations are presented on the slides. So we have different nodes on the network. So this is a linear model in a sense, and we have also the power, the actual power, active power and reactive power, and the voltages of the network. In addition to these constraints, we also have the thermal constraints and transformer constraints and voltage band constraints. The linear model of the building heat transfer, we can think of a building as a state space set of equations, which is the temperature at each time, k plus 1, is a function of the temperature at the previous step, k, and some additional values there. So one of the values that goes into the networks, for example, can be the solar gain through the walls, it can be the window solar gain, it can be ice system, or it can be air conditioning system. The air conditioning system is modeled as this equation in the middle. So the P represents the electric consumption, and U presents the thermodynamic consumption and energy consumption. And the relationship between those is done through the coefficient of performance of the assets. These assets, the air conditioning assets, we can also, knowing their power factor, we can estimate their active power and reactive power of the house by knowing the flexible. The P flex in that equation is the P air conditioning system, P HVAC. And it's assumed that, well, the reactive power is, although it's very small, it is present. The linear model of the air batch HVAC system with the ice storage. So the model is a thermodynamic model for the system. However, we can simplify that by assuming that the ice is always between the state of fully liquid or fully solid, so between 0 and 1. So we can convert that into, again, a state space set of equations that each step depends on the previous time step. And the P air conditioning depends on the amount of ice you have in the network, in the tank, and also the compressor of the asset. And the idea of this system is that it can cool down the house via its tank, via the ice storage, or it can cool down the house via its compressor. So it has the two functionalities. The receding horizon optimization that we used is essentially trying to minimize the cost of electricity for each house. And on the top figure on the slide, we can see the price signal that we use. So we have a 3 hours of peak price followed by shoulder periods and off-peak period during the night time. And at the lower part, we have the IEEE distribution network that we used in our case study. 55 houses in that system were used, and it was assumed that all of them, they have ice storage systems on the network. I will not go through the case study itself because of the time, but it is well documented in the paper. Essentially, we randomly allocate the size of the ice storage system to the houses, and the houses have different sizes and different thermal properties. One of the interesting results that came out of the paper was this figure here. So the red line there is the amount of power consumption of the whole network when we were using ice storage, and the blue line is the base case when it was only using air conditioning system without ice storage. And you can see the ice storage, you'll have a higher electricity demand during nighttime because it's charging the ice tank essentially. But it is assumed that during that time you have maybe plenty of wind or plenty of electricity. During the peak period, however, in the afternoon time, we can see that demand is much less compared to the base case, especially during the actual peak between 16 to 17. Between 16 to 19 in the afternoon, and you can see the demand is significantly less. The graph on the right shows the minimum voltage of the network, so that's at the end of the network, and you can see the voltage is improving a lot during the peak period, and we are ensuring that the voltage remains within the bound of the regulations. In terms of conclusions of the paper, we show that the ice storage is a low-cost solution that can shift cooling air conditioning system successfully. A load aggregator can use this flexibility to manage the distribution network performance, and the result of the simulation shows we can get 66% reduction during peak period at this time. Thank you very much.